Light and atomic spectra. So according to Louis de Broglie's wave theory, light consists of electromagnetic waves or radiation. And all electromagnetic waves are going to travel in a vacuum, which means there's not particles interfering, at 3.0 times 10 to the 8 meters per second. This is the speed of light, and we're going to note that with the variable c. So each complete wave cycle is going to begin at and return to the origin. The origin is going to be our solid line here. The red line is our wave. Our wave cycle is going to keep crossing the origin. And where it crosses the origin is called a node. The crest is going to be at the top of the wave, and the trough is going to be at the bottom of the wave. The distance between the two crests is called the wavelength. That is noted with the Greek letter lambda. Looks more like that. It's hard to see on here. And the amplitude is going to be measuring from crest to trough. So basically how tall the wave is. We don't really look at that very much. We're going to look more at the wavelength for these guys. These electromagnetic radiations are going to include radio, microwaves, infrared waves, visible light, ultraviolet light, X-rays, and gamma rays. If we look at this, you'll notice that as the energy increases in this direction, our wavelength is getting shorter. So the distance between these two crests is very short at our higher energy end. So high energy is a shorter wavelength. And at the other end, where we have lower energy, we're going to have longer wavelengths. So I need you to know that the higher the energy, the shorter the wavelength. The lower the energy, the longer the wavelength. I need you to know that gamma, X-ray, and UV are higher energy, so they have a shorter wavelength. And radio, TV are low energy, longer wavelength. The visible light's going to fall kind of in the middle near the infrared. Purple, violet are high energy, shorter wavelength. Reds are lower energy, longer wavelengths. So I need you to know high energy, short wavelength, that's where you have gamma rays, X-rays, UV, that's where your purple and blues and your visible light fall. Lower energy means a longer wavelength. You're stretching these crests out here. That's where your radio, your TV, and your reds are going to show up. Frequency nu and wavelength lambda of all waves are inversely related. So as we increase one, the other's going to decrease. So here we have a very short wavelength, but we have a higher frequency, meaning it's crossing the origin more often. And when you have a longer wavelength, here we have a very long wavelength, we have a lower frequency. We do not cross the origin as often with those longer wavelength radiations. The product of frequency nu and wavelength lambda is always going to equal a constant, c. the speed of light. Remember, product means multiply. So if you take lambda times nu, you're always going to get the speed of light. Obviously, we're not going to solve for a constant. Constant means it doesn't change. So lambda times nu should always equal 3.0 times 10 to the 8 meters per second. So typically we'll be dividing when we're solving these problems. The SI unit for frequency is a hertz, Hz, but it can also be expressed as a reciprocal second, s to the -1. If you have it in a reciprocal second, it's going to be easier to solve problems that way because the speed of light is a meter per second. So when you have a reciprocal second, it's going to be easier to cancel that second unit out of the speed of light unit. Every element is going to emit light when it is excited. And the atoms are going to first absorb the energy, then they're going to lose that energy as they emit light. So when you're seeing the light, these elements are losing their energy. White light is going to give a continuous spectrum. So this is an example of white light. It's continuous. One color runs right into the next. Elements give a discontinuous or a line spectrum, and that's like these three here. So this first one, this is hydrogen, so you can see hydrogen only reflects certain lights. Neon, and then iron. Iron reflects most amount of light there. The emission spectra of each element is unique to that element. So you can use a spectra to identify an unknown or inaccessible substance. So this is how scientists are able to determine what gases and what atoms are making up stars that are light years away, that we obviously cannot just get on a spaceship and travel to, take a sample of it and bring it back. They're using the light spectra that those stars are emitting so that we can tell what they're made of. So let's calculate the wavelength of the yellow light emitted by a sodium lamp if our frequency of radiation is 5.10 times 10 to the 14th hertz. So remember, C equals lambda times nu. Remember, lambda is the wavelength and frequency is nu. We're obviously not going to solve for the speed of light, but we can say, let's change colors here. We can say that C is equal to 3.0 times 10 to the 8 meters per second, just so we have it listed. We have frequency, which is nu, and they told us that is 5.10 times 10 to the 14th hertz. That means we are solving for lambda. We're looking for the wavelength. So if we have C equals lambda times nu, and we need to get lambda by itself, that means we need to divide both sides by nu. So to solve for lambda, we're going to take C divided by nu. C we know is 3.0 times 10 to the 8 meters per second divided by nu, they told us is 5.10 times 10 to the 14th meters per second. Now, when you're trying to determine significant digits, you need to go by what was given to you in the problem. So in this problem, this is the only value that was given to us, the 5.10 times 10 to the 14th. That value has 3 significant digits. So our answer needs to reflect 3 significant digits. You are not going to use a standard or a constant to determine your significant digits. This guy is a constant, so we're not going to base our sig figs off of that measurement. We're just going to use what was given in the problem. So we have 3.0 times 10, make sure you're using your E key, to the 8th, divided by 5.10 times 10 to the 14th. And 3 sig figs means we're going to report it at 5.88. Make sure you read all the way to the end of your calculator. You'll see an E down there. Remember, that means times 10. And then we're going to make the last part of that number an exponent, -7. And I messed up with my units here. That should not be meters per second. That is a hertz, which is the same as a reciprocal second. Sorry about that. So the seconds are going to cancel out, and we are left with meters for our wavelength. And we will do more examples with this in class.